Thank you for having me. So indeed, I want to try to describe a perhaps strange perspective on field theory, or rather maybe more specifically on the relationship between continuum quantum field theory and its realizations in lattice Hilbert spaces or otherwise well-regulated Hilbert spaces. And I think we're learning new things, non-perturbative things about quantum field theory this way. I guess I should make a disclaimer that it's not yet at the stage of being able to do precision calculations of hadron masses in QCD. Sorry, but you know who knows what will happen. The program I want to describe is based on an exploration of the following idea. I called it a central dogma. So let me say it, and then I'll try to explain what I mean by it and why you should care about it. So the claim is that all of the universal properties of a state of matter are encoded in the reduced density matrix of a ball of a single representative of the state of matter. Okay, so that's a lot to unpack, and let me try to explain. So the picture I want to keep in mind is that I'm always working in some Hilbert space which is finite in finite volume, so something like a lattice. And so this is a picture of the kind of ball I have in mind. And maybe I should say, ideally the Hilbert space is a tensor product Hilbert space, a tensor product of finite dimensional Hilbert spaces. That's my favorite place to be. But I'd like to emphasize that this doesn't exclude gauge theory. Gauge theories can be realized in such tensor product Hilbert spaces and by adding extra degrees of freedom in the UV, which go away at low energies. So what I mean by the word universal here, this is an important word, is properties that are intrinsic to a fixed point of the normalization group. So a given state that might be realized in this Hilbert space is, I'd like to think of it as it lives in the basin of attraction of some fixed point. It may be a zero correlation length fixed point describing a gap phase, probably, or it may be an infinite correlation length fixed point describing a critical point. By universal, I mean properties of the fixed point representative. So this maybe isn't every question you might want to answer, but it's a certain set of well-defined questions. I should also maybe explain the word dogma. So I borrow this notion of central dogma from the molecular biologists, where it was used to refer to the sort of guiding idea that DNA makes RNA makes protein, which generated a lot of important questions and important work. And I guess another aspect of it is that it contains the idea that every cell in an organism contains complete instructions for making the whole organism. So I'd like to emphasize that parallel, that you have some state of matter. I guess ideally I should have drawn the lattice over the whole slide, and I'm only looking at this ball that's part of it. And the claim is that the local density matrix in this ball contains all of the information to rebuild the whole state, to rebuild the whole, everything you might want to know about the whole state. Okay, so I should probably start by saying why you might believe that this principle could be true. This slide is a little bit busy, but the intention is to give a sort of cultural immersion in the way I'm thinking and why I believe this principle. And something I should emphasize at the beginning is that the statements on this slide are not mathematical physics. They're things that mathematical physicists would love to find some hypotheses that would make them true, but they're expectations that we have. So first of all, so notice I haven't said anything about a Hamiltonian so far, but if we do have a local Hamiltonian, then it's in the ground state. So one thing we can do with the density matrix of this ball is compute its von Neumann entropy, the entanglement entropy between the ball and its complement. And the expectation is that in the ground state of a local Hamiltonian, this entanglement entropy will satisfy an area law, right? Basically, the local Hamiltonian encourages the degrees of freedom to be entangled with their neighbors and not with something that's in the middle, something in the middle of the ball is not entangled with something far away, directly. Okay, of course there are some exceptions to this statement. So this is a way to if you give me a state, I can compute the entanglement entropy and ask whether it satisfies this area law. If it does, that's some evidence that it is the ground state of a local Hamiltonian. Furthermore, the reduced density matrix of a big enough ball knows whether the state is gapped or not by computing equal time correlation functions of operators inside the ball but far enough away, which is something we can do with this density matrix. If they fall off exponentially, it's probably gapped. If it's a power law, it's probably gapless. Slightly more refined piece of information. If the ground state is the ground state of a topologically ordered phase, meaning a phase of matter that's non-trivial because it has some excitations that can't be created by local operators, things like anyons, then in addition to this area law contribution to the entanglement entropy, there's a universal subleading term, which is called the topological entanglement entropy, which extracts one piece of information about those anyon excitations of such a phase of matter. So this is exactly a sense in which we're extracting universal information about the phase of matter from the reduced density matrix. So one important exception to what I said about the area law of the entanglement entropy is in the case of the ground state of a 1 + 1 dimensional CFT, conformal field theory, where, as Ross already mentioned in his talk, if I choose, so in 1 + 1 dimensions, a ball is an interval. In that case, there's this logarithmic violation of the area law, but the coefficient is the central charge, which is some property of the fixed point describing the CFT, measuring the number of degrees of freedom. And there's a similar formula for round balls in higher dimensions, which extracts the analogous renormalization group monotone. Okay, but so far I've just been talking about entanglement entropies. Of course, there's a lot more information in a density matrix than just its von Neumann entropy. And one thing we can think about is the log of the density matrix, which is called the entanglement Hamiltonian, as if the density matrix were a Gibbs state for that operator. And well, I guess there's a sort of general conjecture due to Lee and Haldane that, for example, in a 2 + 1 dimensional topological state, that there's a relationship between the spectrum of the entanglement Hamiltonian of a ball and a CFT that lives on the boundary, describing the gapless edge modes that are required by whatever anomalies that state has. Slightly more restricted statement is, using this operator, we can compute its commutator between two regions that are arranged like this, that's some decomposition of the ball, and then take the expectation value in the state that we started with, and the claim is that this combination computes the chiral central charge, so basically the number of chiral edge modes, left movers minus right movers, just from information about the reduced density matrix of a ball in the middle of the state, right? So there's no actual edge, but it says if you did have an edge, it would have to have this chiral central charge. I'd like to emphasize that this principle is more general than just statements about ground states. So one fact that many of you, I think, probably know about is the eigenstate thermalization hypothesis, and this is a consequence of the central dogma. Right? So one way to think about it is, so it says that if I have an interacting enough local Hamiltonian, then a single eigenstate in the middle of the spectrum of the Hamiltonian is enough to reconstruct the whole Hamiltonian. So that is, if I consider the reduced density matrix of any region that's less than half of the degrees of freedom of the system, then it takes one version of this hypothesis is that it takes the form of a Gibbs state where the entanglement Hamiltonian is the Hamiltonian of the region. So in particular, you can extract the whole Hamiltonian from the reduced density matrix, and so that necessarily means that it contains all of the universal information that you might want to know about, because it also contains a lot of non-universal information. Okay, so maybe by now you believe this principle. Do you believe it? What do you think? Well, maybe I should say, yeah, please interrupt me. I don't like talking by myself. It's better if you ask me questions during the talk. Okay, so one consequence, and which is the starting point of this sort of program of this principle, is that for each kind of state of matter, like for liquid topological order, for CFT ground states, for other kinds of things that I don't want to talk about, there should be some kind of conditions on the density matrix that tell you which kind of state it is. Right? Is it a ground state of a liquid topological order phase? Is it a CFT ground state? And so the program is to try to identify such conditions for a category of states. And then there are two ways that you can use such conditions, both of which are kind of merit the term bootstrap, I think. One of them is to impose these conditions as axioms and try to use those axioms to prove structural properties of this universal information. So, like, what are relations between the information we might want to extract? What structure does it have? And the second kind of thing we can do is just impose that condition on density matrices of small systems and try to find representatives of such phases. the nice thing about this is that there was no input of starting with some Hamiltonian, which is, you know, some human-centric parochial thing with Hamiltonians that people like. You know, it just, if we really did identify, you know, necessary sufficient conditions for the density matrix to be, say, a CFT ground state, we could just enumerate all of the CFTs by doing this. Okay, so the goal, so the goal of the program is to understand the structure of this universal information along the lines of the first thing and learn to extract it along the lines of the second thing from the local density matrix. Okay, now I should explain that because of the ambient fact that the universal information about phase of matter is usually encoded in a quantum field theory, I'm relying crucially on this ambient fact for this talk to be relevant for this meeting. Because of that, we can learn something about quantum field theory from doing this. Okay, so that's the situation. And I'd like to explain hopefully 3 cases where we've made some progress towards implementing this story. So the first one is the case of liquid topological order, where I would say most of the progress has been along the lines of the first strategy of trying to identifying some axioms. Actually, Bowen-Shi and Isaac Kim and Kotaro Kato identified a set of axioms which, as I'll explain, are a good starting point for thinking about this problem, from which we can derive structural properties of the effect of the universal description of such a thing, which we expect to be what's called topological field theory. Okay, so that's the first class of things. And so in this case, there's actually quite a lot to say, which I'll try to say as little as possible, because I really want to get to the analog for 1 + 1 dimensional conformal field theory and the much more recent case of conformal field theory in any dimension. Okay, and then there are a few other cases that I will not talk about. Okay, so what do we mean by liquid topological order? Yeah, so a phase with topological order means that, so for now, let's take it to be a gapped phase that has local excitations that you can't create with any local operator. So they have to be created by the excitations are created by some extended operator, which the extent of the operator doesn't excite the vacuum, but the endpoints of the operator do. And by liquid, I mean that the set of topological excitations doesn't depend on the geometry of space. And so this is explicitly intended to rule out the idea of the presence of fractons, which I don't understand from this point of view yet. And in particular, it implies that we expect the low energy field theory, the low energy description to be given by a topological field theory. So fractons are an exception to this expectation that an ordinary topological field theory describes the low energy physics. And okay, so mathematicians have some opinions about what a topological quantum field theory is. Right? They have some definition of what it is. In the case of 2 + 1 dimensions, I think they're on the right track. So there's this thing called a unitary modular tensor category, which I guess was first discovered in the context of CFT by Moore and Seiberg. It seems to do a really good job of being a sort of container for the information about such a liquid topological phase in 2 + 1 dimensions. But it's sort of an empty container that needs to be filled with physics information. In the case of higher dimensions, say 3 + 1 dimensional topological phases, the mathematicians also have opinions, but I would say that it's much less clear whether that's really what describes the low energy physics of liquid topological order in higher dimensions. And so I think in that case, there's really more room for us to learn something about the structural properties of, for example, can we see if the mathematicians' opinions are the right ones? Okay, so given some density matrix on the ball, how do I know if it's the reduced density matrix is some ground state of a liquid topologically ordered phase? And so here's the answer that Bowen and Isaac and Kotaro gave. There are 2 conditions on the density matrix of let's think of it as a small ball, which involve just the entropies of some decomposition of the ball. So divide the ball up into the Chewy filling and the boundary, and A0 will be the condition that this combination of entanglement entropies vanishes, and A1 will be the condition that this combination of entanglement entropies vanishes. So here I'm dividing up the boundary into 2 parts. For any disk of, say, of some radius of a few lattice sites. And okay, I'm going to try to illustrate why these are interesting, but one thing that's interesting about them is that they're self-reproducing. So if I impose this condition on small balls, we can show that they're also true for large balls, for any region of the same topology. One piece of intuition is that you can directly see from this condition that A0 implies the area law for round balls, because you see the entropy of C, you can write it this way in terms of B and BC, but entropies are positive, and so this is bounded by B, which is the boundary of this round ball. Combining A0 and A1 implies the area law a strong form of the area law for all regions, including implying that the subleading term is universal. Okay, so a consequence of A0 is that the mutual information between C, the region inside the Chewy filling here, and A, where A is any region outside of BC, vanishes exactly. Okay, so, and here's in green as a proof of that. And so you can see that this is too strong a condition, actually, right? Because this, in particular, this mutual information bounds correlation functions between A and C. And so this condition is exactly true only at zero correlation length fixed points. So here's a picture of some phase diagram. In each gap phase, there's a unique zero correlation length fixed point, which is sort of the best state to study if you're interested in studying that phase. And only there is this condition exactly true. A better version of the theory would have approximate axioms from which we could show that the conclusions are all still true with some error. But here I'm going to rely on the normalization group to say that if you take big enough balls, you can make this condition more and more true as you get closer to this fixed point. A1, by a similar argument to this, implies that any three regions that are any two regions A and C that are separated by some buffer B form a quantum markup chain. Okay, so this is some quantum information jargon, but the thing you should know about it is that a quantum markup chain is just like a classical markup chain. It means that you can reconstruct the whole state from its parts in a unique way. So in quantum mechanics, this is in general a very difficult problem. If I give you a bunch of density matrices on A, B, and BC, it's very, very difficult to find a density matrix on ABC whose marginals are the ones I've given you. But if you know that it's a quantum Markov chain, then there's a trivial solution, which is called the Petz recovery map. Okay, so that's really the engine for all of the progress that I'm going to say in the next couple of slides. Okay, so given these assumptions, what do we do with them? And well, one answer is the following definition. It's called the information convex set. The idea is to each region of space on which we have such a state defined, define a convex set of density matrices, which I'll call sigma x, which are those density matrices that locally look just like the given state. Right, so here's a picture. Let's take the case where x is an annulus. I cover it with these little balls, and I ask about all the states. Roughly, it just means that they're locally in the vacuum. Right, all the states where on each of these balls, you can't distinguish it from the given state on the whole space. And why this is interesting because it means that although the state is in the vacuum on the annulus, it can do whatever it wants elsewhere. And so in particular, there can be an anion in the whole of the annulus, which is connected by its string operator to its antiparticle outside. And that string operator, although it doesn't matter exactly where it is, it has to go through the annulus and it changes the density matrix of the annulus. Okay, so the axioms imply that this convex set is a topological invariant in the senses that you want it to be true. It doesn't depend on the shape of the region, only in its topology, and it doesn't depend on the representative of the phase that you pick. Okay, and so the idea is that this convex set is a receptacle for the universal data. By choosing different topologies, you encode different information. It's some finite dimensional compact convex set, which means that it's specified by its extreme points. It's something like a simplex or like a block ball. The information convex set of the annulus is a simplex, and the extreme points correspond to the anion types. You can extract the quantum dimension of an anion, of the corresponding anion, just by computing entropies. And the information convex set of the two-hole disk is instead like a block ball. It's the space of density matrices on some finite dimensional Hilbert space, whose dimension is this is interpreted as some set of fusion coefficients. Yes, please.
Sorry, I somehow lost track. What does it even have to do with the annulus?
Good. So sigma of x is this object, this convex set of density matrices. Okay. So yeah, it's some convex set. The picture, this tetrahedron I'm drawing is that convex set.
understand that's a convex set, but
Yeah.
how is it related to an annulus as opposed to something else?
Well, okay, right. So yeah, here I'm trying to define a machine, which you pick a topology of some region, like an annulus or a two-hole disk or something like that, and a state on the ball, and the output is some convex set. Yeah, some finite dimensional compact convex set. And so, yeah, there are two choices for what that convex set looks like. Either it's something like a simplex, or it's like a block ball. Right? The difference is that the simplex has isolated extreme points, and the block ball has a whole block sphere worth of extreme points. Okay, okay, I don't want to get too much hung up on this, but the point I want to make is that in this way, by thinking about this object, which is nice because of the axioms, we can extract the information that the mathematicians tell us we should, right? All the data of a unitary modular tensor category describing this topological phase. And in particular, there's one consistency condition that's easy to prove, is that the dimensions that we extract this way are consistent with the fusion rules. Okay. Okay, in higher dimensions, as I said, it's a little less clear exactly what data we should look for. The axioms, however, generalize very nicely. The only difference is that I need to talk about higher dimensional balls. Again, I divide it up into an inside and a boundary. And so all the basic results that I described hold, except the difference is that there are many more possible regions we can consider. So just to emphasize the variety, we can, for X, we could choose, say, the complement of some knot. Right? Any knot you want to think of, we can think about the information convex of its complement. And this is a huge set of data, which seems that let me just say, there's a bit of tension between the enormous multiplicity of this data for a given state and various classification theorems of topological field theory in 3+1 dimensions, which claim that basically it's just discrete gauge theory. Okay, so a question you can ask is, can we derive topological field theory from this? And I'll just say one example is there's one axiom of topological field theory that the mathematicians like, which is something called modularity or braiding non-degeneracy. It says that every anion braids non-trivially with some other anion. And this is something that we can actually prove from this point of view. So, okay, so maybe they're on the right track, I guess, is the conclusion here. Good. So now, if you didn't like what I just said about topological field theory, you can just totally forget it. The point I wanted to make is that there is an instance, there's a set of examples where this strategy has been useful, it was a good idea, and now I want to do a slightly crazy thing and try to apply it to conformal field theory. Sharon, please.
So, about the proof for remote interactability, is that in 2+1D or in general?
Yeah, so in 2+1D, it's a statement about anyons, really particles. But in general dimensions, it's a much more general statement, set of statements about various kinds of regions pairing with other kinds of regions, yeah. So in 3+1 dimensions, for example, particles can pair with loops. And
it could also be something more complicated.
Yes.
Like triple loop.
Yes. Yes.
And that all follows from
Okay, I won't say that we've proved the most general thing, but there's a very general set of statements, yeah, about various kinds of excitations that pair with each other. Actually, I had a table that I removed from my slides that I can show you of the things that we've shown. Yeah. And actually, that's the reason that result hasn't appeared yet, because we made the mistake of trying to prove a very general thing. Okay. Yes, please. Oh, no, that's a great question. Yeah, so the question was about a transparent fermion. So yeah, indeed, I'm assuming that in what I was just saying, the assumption is that it's a bosonic Hilbert space. Yeah, in fact, it's in some ways an open question to generalize it to the case where there are fermions as well. That's a good problem. Somebody should work on it. Yeah. Good. Okay, so here's the central dogma again. And as I said, if it's really true that you can extract all the universal information from the reduced density matrix, there should be some condition on the density matrix that says that it's a CFT. And so let's try to ask what that condition is. So I already mentioned that the entanglement entropy of an interval in the ground state of the CFT looks like this. This isn't quite enough. There isn't a condition just on the entropies that does what we want. But we actually know the whole entanglement Hamiltonian for the ground state of a CFT on an interval. And it takes this very simple form, which involves the actual Hamiltonian density of the CFT and some function associated with the region, which is just locally quadratic. So it's only non-zero in the region, and it's zero, and it vanishes linearly with slope 1 at the boundary. Okay, and so from this observation, consider the following combination of things. So consider three regions defined by, by these 4 points that defines a cross ratio. And it is a fact that if I choose this function for each of these regions, that this linear combination of the functions vanishes for all x. It's just, yeah, you can see it from this picture roughly. That implies that if you take this particular linear combination of entanglement Hamiltonians in the ground state of a CFT, it's a C number, right? The operator part, just the whole thing is proportional to h of x, and the coefficient of h of x vanishes, and what's left is just this identity bit. And the coefficient of the identity is h of eta, which is just the binary entropy function, as if the cross ratio were a probability between 0 and 1. Okay, so far I've been writing formulae in the continuum. This is just a fact about the continuum CFT. But to actually make sense of it, for example, to compare to a quantum critical lattice model, let's divide up the circle into equally spaced intervals and regard each interval as a site. So it's really an infinite dimensional Hilbert space on each of these sites. And in the lattice, the equation, actually, if you check this operator equation that I wrote, it's actually not true. And the reason it's not true is because on the lattice, the density matrix, the local density matrix can have a kernel. And so when you take the log, bad things happen. But the kernel goes away if we act with the density matrix on the state itself. And so a slightly weaker statement, which we call the vector fixed point equation, is what you get if you take this operator equation that I wrote here and act on the state. And this equation is really true. So for example, in the criticalizing model, we can study the error in this equation, which is, so it says that this operator acting on the state is a number acting on the state. It's almost like an eigenvalue equation, except the operator is determined by the state. And so the condition for this to be true, it implies, for example, it implies that the variance of the operator k vanishes in this state. And we can check that that actually becomes more and more true as the system size grows. So this is a weaker condition than the operator equation I wrote, but it's still a very strong condition because it's an equation for n components in an n-dimensional Hilbert space. Okay, and so I claimed that all the universal data is encoded in this density matrix, but what is the full set of universal data? I didn't tell you that. And I don't know. That's actually part of the problem. However, I can show you that this is true by using the reduced density matrix to construct not only the whole ground state, but a Hamiltonian whose ground state it is. Right? I didn't start with a Hamiltonian. I started with a state, and I end up with a reconstructed Hamiltonian, a local Hamiltonian. And okay, so let me show you how to get the ground state. So I emphasized that this axiom A1 in the topological case, its role was to allow us to merge regions together. If I give you the density matrix of AB and the density matrix of BC, this quantum Markov condition tells us we can reconstruct the whole state. This vector fixed point equation is an analog of that, because we can solve it for ABC in terms of its parts. And this is a condition that reduces to the quantum Markov chain when eta goes to 0. So we can reconstruct the whole state from its parts, which I emphasize in general is a very difficult problem. Okay, so here's reconstructing the Hamiltonian. In the same way we can find a linear combination of these functions which was 0, we can find a linear combination of these functions which is 1. So when I add them up, it just adds up to the Hamiltonian. And that linear combination actually just turns out to be the entanglement entropy of 2 intervals minus the entanglement entropy of 1 interval. This turns out to be a positive operator, and we can show that if a state satisfies the vector fixed point equation, it's the ground state of this operator. There's a similar formula for the rest of the global conformal generators. And I think probably the best thing about this is that it actually works, even for really ridiculously tiny systems. So people have been talking about, I don't know, enormous systems that they've been doing DMRG on. Here's the Heisenberg chain on 8 sites. Here's the spectrum, just in exact diagonalization, and the circles are the actual, are the spectrum of the lattice model, and the x's are the spectrum of this operator, reconstructed from the ground state. 8 sites, yeah. It works very well even for 4 sites. And so here's a wonderful surprise. Okay, I'm going to have to stop soon, but this is maybe the most important picture. This condition, this vector fixed point equation, is the condition to minimize a certain linear combination of entropies. And the value at the minimum determines the central charge. So there's some function on the space of states whose critical points satisfy this condition. it's very natural to conjecture that the critical points of this function correspond to a normalization group of fixed points. And that, moreover, the shape of the function near the fixed point has some information about the spectrum of the CFT. And this leads to a picture where we can replace each of these intervals. So in the continuum, it's in infinite dimensional Hilbert space, we can replace them with just a single qubit and restrict ourselves to translation invariant states. And even, let's also impose time reversal, so they're real wave functions. So it's some 5-dimensional space of states. And we can just find all the critical points of this function on the space of the 16-dimensional Hilbert space. And amongst the critical points, we recognize several of our friends. So there's a state which has a central charge that's a little bigger than a half. There's some states that have central charge a little bigger than 1. And I can confidently identify these with these CFTs because from the state on 4 sites, we can reconstruct a local Hamiltonian, which we can then study on a larger system. And the spectrum, well, the spectrum looks like this. And something I'd like to emphasize is that the multiplicative renormalization of this reconstructed Hamiltonian is completely fixed. So you can make a 0-parameter fit of the CFT spectrum. You don't need to find where the stress tensor is in the spectrum, which is generally actually a pretty high level, so it's kind of hard to do. Stop talking. Okay, yes. And so this is actually a very practical tool for numerical searches of CFT. And let me show you, so here's a picture of some lattice model that my student Zhang wanted to study. And here's a plot as a function of 2 parameters of the error, the violation of the vector fixed point equation. The places where this thing is black correspond to fixed points. The places where it's not black correspond to regions in between them. And so you can see there's a paramagnet out here. You have to go over a hill to get to this circle, this ring of Ising critical points, and inside there's another gapped phase. And then the value of the central charge, you can read off from the picture. It's definitely not as precise as the method that Russ used, described for drawing a picture of the phase diagram yesterday, but it's much, much easier. So this is all just 8 sites. Okay, I'm going to stop. If somebody asks me, I'll say something about higher dimensional CFTs, where things also seem to work. Maybe I'll just say one more thing, which is a fantasy of my wonderful student David Lin, whose insight it was to think about this vector fixed point equation, is the following. The story I told you plays actually very nicely with a different kind of bootstrap, this Hamiltonian bootstrap, where one looks for reduced density matrices that extremize some given Hamiltonian. Yeah. In that case, the thing you're not guaranteed is that you can glue them together into a big state. And so you're extremizing in some sort of auxiliary space of states that don't exist. But if you can combine that with a local condition that guarantees that it's a state of the kind you're looking for, you can really make a guarantee about that, the state exists and you're making a good bound on the energy. So you could imagine in the future that such a method could tell you something about, certifying a gap in a theory, some kind of, perhaps some regularized version of Yang-Mills theory. I think it's a good fantasy. Okay, thank you for listening.
Awesome talk. We have time for some questions. I can get things going if people need a little time to digest. So suppose I have a C equals 1 compact scalar. There should be an exactly marginal direction. Can you see it? And how do you see it from your little 4-state thing? Or
Wonderful, wonderful. Yeah, so this question really confused us for a while. Because, so I mentioned, so I drew this picture of the space of states of 4 qubits.
Should be some flat,
Exactly. And you notice that there's no line of fixed points in this picture. There are 2. In fact, we realize only exactly 2 of the points on this equals 1 line. Exactly in this.
Right. That's what drew my eye to it.
Yeah. So in fact, yeah, indeed. So you have to go uphill to move along that line. It says that on 4 qubits, you can't fit all of those CFTs, right? So something you might notice is we don't find all the CFTs, right? We find only a certain list of them. And you can ask, well, what determines which ones we find? Well, one piece of data is when we replace the qubits with 3-state systems, we find a few more CFTs, right? We find 3-state pots, we find the tricriticalizing model, and we find a few more points on this equals 1 line. And so one condition is we're starting from small values of the central charge and working our way up as we increase the local dimension. Another condition is that the states that fit well in a small Hilbert space are ones where there are no primaries of very small dimension. So, for example, if you move very far out on the line of C equals 1 theories,
right,
the winding modes come down, or
yeah,
the momentum
you
modes
get
come down.
more and more and more. Yeah, I understand.
Those don't fit, right? The error grows. Like, for example, we can study the family of ground states of the XXZ model as a function of the parameter delta, which interpolates between these. And you can see that when the radius goes to 0, the error grows dramatically. But on the other hand, we can find a T in the space of states that approximately satisfy the vector fixed point equation. A T corresponding to the place where the circle line connects to the orbifold line. We have not yet fulfilled Lance's request of finding the Ginzburg archipelago. Yeah, we had some conjectures for isolated fixed points that have C near 1, but so we've been actually implementing this search, and well, there's a lot of states, and we're sort of working our way up in the values of the central charge.
Great, thank you. I saw a question from Yuya a second ago. Yuya, there's a microphone behind you.
So when QFT over interest are having some symmetry, where does that data are encoded in this case?
Great. Yeah. So yeah, I guess at a meeting about generalized symmetries, I should have said something about symmetries. Yeah, indeed. So there was yeah, all the symmetries in this talk were emergent. Certainly, for the case of gapped states, you could imagine a version of the program where you impose some extra axiom that assumes that there's some given symmetry and search for states that satisfy that. In the case of CFT, I don't know yet. Yeah.
Also for the system, for example, can we also specify any symmetry fractionalization data, for example?
To specify symmetry fractionalization data, I guess the way that I was thinking about it, I would add an extra condition that my density matrix is invariant under some, say, unitary symmetry operator. And then, given the state, it would be an output. What's the fractionalization data? Yeah, we don't know how to do that. We've thought about it a bit. Yeah, my student Xiang has made some progress on that question, but I don't have a good answer. Yeah.
Is it possible to extract estimates for the scaling dimensions of these CFTs?
Yes, that's right. Yeah, so good. So as I said, this so this is a picture of the reconstructed spectrum. And actually, so you notice if you look at the units here, these are not the dimensions of the primaries of the operators in the Heisenberg chain. They're rescaled by some number. The randomness of that number is the fault of Heisenberg. It's the fault of the lattice model, right? So actually, the reconstructed Hamiltonian is rescaled to match the lattice model there's one number. If you wanted to get the list of primaries, I mean, we're studying the theory on the circle, right? So it's just radial quantization. So if you want to get the list of primaries, you should just use the reconstructed Hamiltonian using the formula that I wrote. That's it.
So then can I ask if it's possible to combine this with the same conformal bootstrap?
Indeed, I think it's a complementary set of information, which I look forward to some fruitful interplay there. Yeah, indeed.
Can you go to the slide where you have that table of XX model and so on? Yeah. So I have a follow-up question of Alex's question. Why is ferromagnet on the table? I thought this is our old relativistic.
Great. So you'll notice that in the conjecture I said critical points of this function, I didn't say CFTs. I said they correspond to RG fixed points.
But some of the criterion you imposed, didn't they assume relativistic symmetry?
The only condition I'm imposing on states in this list is that they're extrema of this function, right? Which means that they satisfy, k delta on the state is proportional to the state.
But then what do you mean by C in the ferromagnet?
Great. So by C, I mean, as I said, if, k delta on the state is proportional to the state, there's something on the right-hand side. If the state is the ground state of a CFT, the thing on the right-hand side is C times H eta over 3. Yeah, so that's what I mean. That's what I mean by C in that case. So indeed, we have to distinguish between gap fixed points, like the things in black, and CFT ground states, which we do by reconstructing the Hamiltonian and studying it on slightly larger sizes and seeing if it's really gapless.
The ferromagnet is gapless.
It has a degeneracy. I mean, seeing if it really has the spectrum of the CFT.
Is this function related to its approach called C-theory?
Great. So good. So indeed, you could ask me, so a function with exactly the properties that I was hoping for here is Zemlyaško's C function defined not on the space of states, but on the space of coupling constants, or of relativistic quantum field theories, right, in terms of some expectation value of two-point function of the stress tensor. If the thing I said about, okay, so in general the answer is I don't know, but if the thing I said about, okay, let me say it this way. The thing I think is true is that near the critical points, in the large system size limit, the local information is the same. I think that we'll be able to extract so there is definitely a relationship between the Hessian of this function in the neighborhood of a critical point and the Hamiltonian of the CFT. So in particular, it commutes with the reconstructed Hamiltonian. The number of negative eigenvalues of the Hessian, even in small systems, agrees with the number of relevant operators. Away from the critical points, I don't know. Yeah. Maybe one thing I should say is if we restrict ourselves to relativistic systems and take a particular limit of eta, this function actually has a close relationship to the C function defined by Cassini and Huerta, which they proved is monotonic in relativistic theories. Yeah.
Other questions? Okay, I have one on this slide. What is if any, what is the physical meaning of the maximum point?
I don't know. It's so yeah, it's some very special state. Actually, I think it's something like a perfect tensor, the wave function. So it has maximal entanglement along every cut, something like that. So the entanglement Hamiltonians all vanish. Is the reason it extremizes this condition. I don't think it has a continuum limit. Yeah. It means you've run out of room, I think, is maybe.
Okay. Good. Okay. We see another question.
What happens with this table when you go to more sites?
Yeah, okay, good. More sites. Okay, good. So yeah, so the direction in which we've been going is not more sites, but more degrees of freedom at each site. Larger Hilbert space at each site. In that case, we find more CFTs. Like I said, we find a few more minimal models. We find some more. We find some states with C bigger than 1. I'm optimistic we'll find the H group CFT soon. Yeah, and actually, I have to say, I still have some optimism that we'll find a CFT that nobody's found yet. Right? There's no classification of conformal field theories in 1 + 1 dimensions. Right? For C less than 1, Steve classified them. Yeah, but for higher dimension, for higher C, we don't know. Right? Eventually, we'll find Calabi-Yau sigma models. Yeah. But okay, but if we had more sites, actually there's a tricky thing, which is if I have more than, so when I have 4 sites, there's exactly 1 vector fixed point equation I can impose. Because they're related by purification move. If I have 5 sites, there are 3, because I can divide it up into, different combinations. And I think we can show that there's no state that exactly satisfies every vector fixed point equation on 5 sites. That's a condition. So that's something that can only be satisfied by the continuum Gracier wave function. So we'll have if we want to add more sites, we have to make a choice about which ones we impose. So there's a slightly more complicated question. It may be a good idea to do that instead of what we're doing. I don't know.
Okay, I think we should thank John for a very stimulating talk.